All right, number 4, we're going to do linear regression. So we can see here that in this question we have, we're looking at houses, and our two variables are how large the houses are, how much living space they have, measured in hundreds of square feet, and how much those homes sell for in thousands of dollars. So for example, one house had 1,400 square feet of living space and sold for $178,000. Another one of these houses had 1,900 square feet of living space and sold for $275,000. So what we want to do is determine what kind of linear relationship exists between our two variables. Now, before we calculate that linear regression model, that line of best fit between these data points, we have some informal methods. So we have our formal method, which is finding the linear regression model. Our informal methods that we do first, we have a visual method. We can make a graph, and we can compute the correlation coefficient. These will give us an idea of whether there exists a linear relationship and what kind of linear relationship there is. So our visual method is we can make a scatter plot. So for example, I'll give myself a little more space for that. Let's see, so I can make a scatter plot of my x variable, which is living space, and my y variable, which is selling price. And all I want to do is graph these data points. So each row here is one ordered pair, or one data point. So my first house, I'll start at 14, 16, 18, 20. My first house had 1,400 square feet of living space and sold for $178,000. So I'll start at 180, 200, 220. So my first house will be somewhere right here. Second house, 15 and 230, will be somewhere here. Third house, 17 and 240, be about there. 19 and 275 will be up here. And then 16 and 200 will be about here. So the question we want to ask is, does this relationship look somewhat linear? Can we draw a line of best fit through this data that captures the relationship? And I mean, we can see here, we can draw a pretty decent line of fit through this data. In general, it looks like the bigger a house is, the more it sells for. So it looks like there's a linear relationship. All right, so then that's the visual method done. Next, we can do our computational method, which is just calculating the correlation coefficient. So let's give ourselves some more space to do that. I'll move down here. Okay, so for the correlation coefficient, first of all, we typically use the letter R to refer to the correlation coefficient, and it measures or it tells us whether there is a linear association between our two variables. And we'll get a little bit more into how to interpret it in a few minutes. Let's just calculate it first. So our formula is we take the sum of squares, that's what SS stands for x and y. Then we take the sum of squares for just the x's, square root that, multiply it by the sum of squares for just the y's. And let's write out our formula for each of the sums of squares. So our formula for calculating the sum of squares for x and y is we take for each xy pair, multiply the x and y value, and then add all those products up, and then subtract the sum of all the x values times the sum of all the y values divided by our total sample size. Sum of squares for the x's looks pretty similar. Now instead of multiplying the x and y pairs and adding them up, we're just going to, for each row, square the x value, then sum all the x values and square that sum and divide that sum by our sample size. Sum of squares for the y's looks exactly like the one for the x's. We're just going to replace them with y's. All right, so let's go ahead and calculate each of these quantities so we can find our sums of squares and then our correlation coefficient. Now, one way to keep organized that I find really helpful when we're working with all these different kinds of quantities is to make a nice table. So all I'm going to do is take my original table and just, add a few columns to it. Okay, so for example, to calculate the sum of squares for x, y, I first need to find this quantity. I need to, for each row, multiply x and y and add those products up. So I'll add in a column and call it x times y, and I'll just go across and multiply. So 14 times 178 is 2492. 15 times 230 is 3450. This is 4080. 19 times 275 is 5225. And then 16 times 200 is 3200. Then I need to take the sum. So let me just add on an extra column. And so I'll add up all the xy's. 2492 plus 3450 plus 4080, blah, blah. This sum is 18,447. All right, then the last two sums I need for sum of squares for x, y is I add up all the x's. So I just add up this column, all my x values, 14 plus 15 plus blah, blah, blah. And I get that the sum of the x values is 81. I'll also need the sum of the y values. If I add up, just these y values, the sum in this column will be 1123. All right, so that's everything that we need for this quantity. Let's go ahead and calculate all the intermediate quantities for the other sums of squares. So for the sum of squares for the x's, we need to add up all the squared x's. So I need to square each x value. So this is 196, 14 squared, 15 squared is 225, 17 squared is 289, this is 361, and 256. So then the sum of all the x squareds is, let's see, I think this is 13, 27. I already have the sum of all the x's. So now I can move on to my last sum of squares, and for that I'll need the sum of all the y squareds. Let's see, this, I'm going to go in the y column and square each of these. Let's see, 178 squared is 31,684. 230 squared is 52,900. 240 squared is 7,600, and then 275 squared is 75,625, and then 200 squared is 40,000. So then the sum of all the y squareds is a big number, 257,809. All right, so now I have all my quantities I need to calculate these sums of squares. So I'll bring these formulas down here. All right, so let's work with the first one here. I need to take the sum of all the x times y's, which is right here, 18,447 minus sum of all the x's times the sum of all the y's, and divide it by my sample size. There are only 5 houses, 5 rows. I have 5 pairs here, right? So that is divided by 5. If you plug this into your calculator, you should get 254.4. Okay, next, sum of the squares for the x's. For, let's see, the sum of the x squareds is right here. Sum of the x's squared is 81 squared. Be careful about these parentheses. These are 2 different quantities. This is, you take each x, square it, and then add all of those up. Here, you're going to add up all the x's and then square. So just be careful that you don't mix up the 2. Oops, and then I'm going to divide this by 5, and I should get 14.8. Okay, lastly, take my y squareds, the sum of the y squareds, which is 257,809. Subtract the sum of the y's and square those. Divide by 5. If you do that, you should get 5583.2. We're not quite done yet. Remember, we wanted to calculate the correlation coefficient, which was R. So now, all we have to do is take these sums of squareds and plug them into our formula. So I should get 254.4 divide by 14.8 square root times the square root of 5583.2, and you get 0.89. One way to check if you've made a mistake in calculating your correlation coefficient is that this R value should always be between -1 and 1. If you get anything outside of the range between -1 and 1, then you've made a mistake and you should go back and check your work. All right, so now we've finished our computation. All that's left is to interpret our correlation coefficient. And when we ask you to interpret the correlation coefficient, we're asking you to address 3 things. 1, is the correlation between x and y positive or negative? And here, r equals 0.89 is positive. So there's a positive association between our x and y variable. What does it mean for there to be a positive relationship between two variables? That means that as x increases, y will also increase. Or, in other words, as x decreases, y will decrease. Basically, if two variables are positively related, they move in the same way. As one goes up, so will the other. If x and y are negatively related, if the correlation coefficient is negative, that means that they move in opposite directions. So as x increases, y would decrease. That's our rule of thumb for interpreting. This is important to remember. So that means that as living space increases, so will selling price. So I've determined that it's positive and I've interpreted what that means. Next, I need to answer, is the linear association strong, moderate, or a weak association? Our rule of thumb here is, let's see, if r is equal to 0, there is no relationship, no linear relationship, I mean. I'll just clarify, when we're talking about the strength, that's referring to the strength of the linear relationship. So if r is 0, that means that there's no linear relationship. If r, the absolute value of r is less than 0.05, we say there's a weak linear relationship. If the absolute value of r is greater than 0.75, we say that there's a strong linear relationship between our two variables. And if r is between, the absolute value of r is between 0.5 and 0.75, we say that there's a moderate linear relationship. So these are our rules of thumb for interpreting our correlation coefficient. So in this case, our r value was 0.89, so we would conclude that there is a strong linear relationship between selling price and living space. So don't forget to use this word for whether it's strong, moderate, or weak, and this word linear. All right, so that finishes part 4A.